Chapter 11. So chapter 11 is actually a really short unit as far as AP curriculum goes. If you go to look at your textbook, chapter 11 is actually quite large. But don't go look at your textbook because it's full of a lot of concepts that we don't need to know. So whenever I made your OWL this time, OWL started out with 54 modules. By the time it got to you, you had 12. The reason for the difference in the two units is because solutions, the AP test has finally decided to go to one consensus on we're only going to calculate concentration in one way. There used to be 6 ways to calculate it. Now we're only going to focus on molarity. There's other ways to do it like molality and percent by volume and things like that. We just don't have to know those things anymore. Okay, we're going to focus on one unit and that should help centralize all the different information in chemistry as well. There's other concepts in this chapter such as freezing point depression and such like that we're also not covering because it's not considered to be part of Chem 1 in college, and the AP test is supposed to prepare you for Chem 1 in college. If you were to CLEP the AP test, therefore you should be able to get out of that course in college. So when we condense what is left, really all we have is a focus on what is a solution, what makes it up, and why do things mix, and the energy involved. So that's the only things we're going to focus on. Very short. So the first thing I want to do is actually go look at a classification of matter chart in the end of your notes to look at where a solution falls in our classification of matter. So if we look at a classification of matter chart, the way I want you to visualize this is I give you matter. Matter is anything that takes up space. I put it in your hand. Okay, you look at this matter and you decide first, is this made of only one pure substance? So is it only one type of compound or one type of element? Or is it made of several types of compounds and or elements? Okay. If it's made of several types of compounds and or elements, then we have a mixture. Now this mixture could be broken down, okay, can be separated into pure substances. So I'm going to look at the pure substances very quickly. A pure substances, it's just made of one thing only, either one pure compound or one pure element. These compounds could be further broken down into one pure element. This would, of course, be a chemical change occurring here. Okay, our compounds can be defined as a molecule if it's covalent. Now, we don't do a lot of focus on this, but just so you know, a molecule is actually only considered to be something that is covalent. So I'm going to write that here. Very rarely would you need to know this distinction. It's misused often, so I'm not going to force it on you. But just so you know, in some readings, sometimes when you question why does it call this a molecule and this a compound, that's why. That's also why when we say intermolecular forces, we're really talking about molecules, so we're talking about covalently bonded compounds. We're not just talking about compounds in general. So intermolecular forces generally, they really only apply whenever we're talking about covalent compounds. Otherwise, we're talking about ion attractions in ionic or the electron C in metallic. Our networks, this is really where we have our metallic and our ionic. These are more distinguished as networks, okay, where they have a set arrangement based off of these electrons. Okay. All of these are made of atoms, and when atoms gain or lose electrons, we call them ions. Ions will become important when we're talking about solids. So let's go back to the matter that's in your hand. You look at the matter in your hand, you can tell or you are told that there is more than one pure substance in there. If you can visually tell where one compound ends and the other compound begins, visually, like you look at the wood grain on the table in front of you, you can visually see where one compound ends and the next compound begins. That is heterogeneous. Hetero meaning different. You see the differences. If you look at it in your hand and you cannot visually see the difference, so someone gave you a beaker with salt water, you can't see where one Na ends and one H2O begins. If you look at the air around you, you can't say there's a diatomic oxygen, there's an argon, and over there is a nitrogen. All you see is air. Well, you really don't even see that, but you know it exists around you due to the fact that your hair blows, right? So we have this solution around us of air, which also gets us into the fact that a solution is not just a liquid state. So we're going to get back into that. But remember, air is a very good example of a homogeneous mixture, and we call a homogeneous mixture a solution. Okay? A solution is uniform throughout, and a solution is made of a solute that is dissolved in a solvent. Often our solute is an ion, okay? And often our solute is going to be one of our soluble ions, and let's go ahead and put those here as a good reference for later. Our soluble ions, okay, Na, K, NH4, and NO3. Now, of course, there are other soluble ions. These are just the ones that we are always soluble. These are the only ones you have to have memorized. Chlorine is pretty often soluble, but there are exceptions to it, and we don't really force you to know that. So what we force you to know is these. Otherwise, you have to be given more information to know, well, does this apply as a soluble ion or not? So where we're focusing right now is on solutions. So a solution is a homogeneous mixture of two or more substances in a single phase. We do not say that a solution is just liquids. It does not have to have liquids. Air is our perfect example of a solution. Now, the reason why I have to distinguish this is because we often, when we say solution, we always say aqueous. But aqueous is a type of solution. It's a solution made in water. AQ, aqueous solution, a solution in water. But that's not the only requirement. We can have solutions made between a gas and a solid, neither one of which would be ever in the liquid phase. The two combine to make a solution that is a solid. Such as if you put hydrogen gas on platinum, so our solution is a solid that's formed. And it was formed by our gaseous hydrogen and our solid platinum. So if we're not just talking about liquid, then that kind of middle school concept of solute and solvent that really only applies to water doesn't work. We always just think of water as the solvent, always universal solvent. Which universal solvent is horrible that we teach you. Because today we're going to learn it's not a universal solvent. It's universal for anything that's polar or ionic, but it is horrible when we talk about nonpolar. So how are we going to define solute and solvent? Well, it's just going to be by the amount present. A solute is whatever we have less of. Okay? Therefore, it is going to be the thing that is dissolved or the dissolvee. Solvent is in greater concentration, it is the dissolver. So solubility is if we take into account this solute and solvent ratio and what's occurring here. Solubility is the maximum amount of material that will dissolve in a given amount of solvent at a given temperature to produce a stable solution. The stable part's very crucial. In other words, that makes our solution saturated. We're at our maximum. Okay? Our solubility rules can tell us which ones of these ionic compounds will be in a solution. Molar solubility is if we use this concept of how much and specifically focus on the moles. The number of moles of solute that will dissolve in exactly 1 liter of solvent. Okay, and this is our molarity. We use a capital M or the square brackets. Get used to these. Any number written inside a square bracket, especially in chemistry, means its concentration. So we have 3 types of solution: saturated, unsaturated, and supersaturated. Let's focus on the 2 that make common sense just based off their names first. Saturated solution and unsaturated solution. A saturated solution is a solution that contains the maximum amount of solute that will dissolve at a set of pressure and temperature conditions. Saturated solutions are at dynamic equilibrium. I'll come back for that term in a second. With any excess undissolved solute present. The solute particles dissolve and recrystallize at equal rates. That's what this dynamic equilibrium is referencing. Dynamic meaning our changing equilibrium, our dynamic equilibrium is where we have an equal rate of our solute plus our solvent combining to make a solution. Solute plus solvent combine to make solution. An equilibrium is an equal rate going forwards and backwards. So we have solute plus solvent combined to make solution, but because we're already at our maximum, by making more solution, we also create the reverse process. Our solution breaks apart into our solute and solvent. So we are equally creating more solution and breaking back down into solute and solvent. And I've got a visual to go with that in a second. Our unsaturated solution is a solution containing less than the maximum. So we have less than the maximum amount of solute, therefore we can dissolve more solute. So let's look at the pictures down here for unsaturated and saturated. So imagine these being salt crystals added to water. It could be any solute into a solvent that it will dissolve in. So we add more of our salt into here, and notice how nothing is forming on the bottom. It's because this is capable of dissolving more solute. We're unsaturated. So the only thing that's occurring here is dissolving. So what's occurring here is dissolving. Whereas over here, in between here, we can see that there must be some dissolving occurring. We don't see the crystals falling all the way to the bottom. But at the bottom, we also have crystallization. Crystallization here. So as we add these crystals, we have dissolving occurring, but at equal rates, just as fast as we dissolve crystals, we produce crystals. Because there's not enough solvent to separate all of this solute. So if we have solvent up here separating these particles or these ions or whatever it is we're adding to it, whatever that solvent that is dissolving the solute up here, there's not enough solvent down here to keep everything separated. So if we can't keep the ions separated from each other, they'll just recombine, form a crystal. So we have crystals. So now let's look at the concept of supersaturated, which sounds like an oxymoron. We just said that saturated is our maximum. So how can we have a supermax? Well, we have a supermax prison, so there must be possibilities of this. The supermax here are our supersaturated. Our supersaturated solution is a solution that has been prepared at an elevated temperature and then slowly cooled. So what it is we actually make the solution saturated at an higher temperature, okay? And then when we cool it, we've technically broken the rule of saturated. At saturated, it was the maximum amount at that temperature. But because we don't disturb anything, because we don't have these molecules moving, and so the solvent is in this very fragile ability of holding all this solute dissolved in the solution, it can stay as a solution until some sort of agitation occurs, because this is very unstable. These solvent molecules are barely holding all of the solute apart because there's more than should be capable at this temperature. There's not enough energy to keep these solute ions or these solute molecules apart. They're now being attracted to each other to form crystals. So all that it takes is some slight agitation or a seed crystal. So you bump the table, you stir it, or you drop a crystal in there for the ions to be attracted to, and you're going to get a crystal forming really quickly. So this will cause all of our excess solute to crystallize out of the solution, leaving a saturated solution. So all of that excess solute that was being suspended in this solution on its very unstable grounds, the second you added something, you added some agitation, or you added a crystal for these crystals to form on, all of that excess solute immediately pulls out of the solution, and what's left is saturated again at that temperature. So our picture here shows that. So we're adding crystals But whenever you agitate this, so this was already at its maximum, all of that excess solute is going to make us some very large crystals very quickly. So a way to show this unsaturated and supersaturated and just saturated solutions, we can look at our solubility charts. So this solubility chart shows the solubility of several different substances. The line is the maximum. So the line is saturated, just saturated. So if I am looking just at sugar, we won't consider the rest of these right now. If I say I have a solution at 40 degrees Celsius and it has a solubility of 180, which is just how many grams per grams of water, then I would say it's unsaturated. I could still add more grams to the water until I hit this line. At this line, I would call it saturated. This should be the point at which you can't add any more grams of solute. However, if I take a supersaturated solution and I graph it on here, you will be above the line, because this line says what the maximum should be. If you've exceeded that, then your data point would be above the line, and that's how you would identify a supersaturated solution. Okay, it is above that maximum line, it is unstable, it doesn't take much, and it'll fall immediately back down. Okay. So some terminology we're going to need here is miscible and immiscible. The easiest way to do this is miscible is mixable. Okay, so I'd write that word there. Miscible is mixable. If the two things will mix together, then it's miscible. If they will not mix together, it is immiscible. So water and oil. So for our concentration for solutions, all we have to know is molarity. Molarity is our moles of solute per liter of solution. To be picky, just so you know, it is temperature dependent, but that's not something you'd be tested on. So molarity is moles of solute over liter of solution. You should be able to apply that information to solve this one problem. I gave you the answer here, so you should be able to check it and see if you get it right. So energies involved in solution formation. So when a solute is dissolved in a solvent, the attractive forces, when a solute is dissolved in a solvent, the attractive forces between solute and solvent, particles are great enough to overcome the attractive forces within the pure solvent and pure solute. What this means is that they are more attracted to each other than they are to themselves. I want you to add that right here. They are more attracted to each other than they are to themselves. That is what will decide whether or not they are miscible or immiscible. That's what decides if they are mixable. So if you have two things that are polar, then they're going to be attracted to one another. So that makes sense as to why they would mix around each other. If you have something that is nonpolar and something that is polar, the polar thing is going to be more attracted to itself than it is to this nonpolar thing. So if something is polar and nonpolar, they are immiscible, because the polar thing is more attracted to itself and pulls to itself, and the nonpolar thing will be still just as attracted to itself and pull to itself. But the main thing we're going to focus on is what is the polar thing doing, or what is the ionic thing doing. So if I put something ionic into something that is polar, well, those ions, those positives and negatives, will be attracted to the positives and negatives in that polar solvent. But if I put something ionic into something like oil, if I try and put salt into oil, those ions, that positive and negative, aren't attracted to the oil at all. So they won't dissolve in oil. They are immiscible. They are not mixable because there's no attraction between them. Those intermolecular forces that are holding the oil to itself aren't going to get broken. And the ionic attraction, the lattice energy that's holding the salt to itself, isn't going to get broken. And that's the first step of creating a solution, is we have to separate our solute, separate our solvent, and then everything can mix together. And we'll look at the delta H for that in a second. So if we break this down, that means our substances with similar types of intermolecular forces dissolve in each other which simplifies to like dissolves like. So polar solvents dissolve polar or ionic solutes. They do this by either dipole to dipole or dipole to ion. It depends on what your solute and your solvent are. But all of this has to do with attractions between positives and negatives. Whereas nonpolar solvents dissolve in nonpolar solutes because of London dispersion forces. If they both only have London dispersion forces, then they will both be attracted to one another. But something that's polar is going to be much more attracted to something that's polar like itself than it's going to be attracted to something that only has London dispersion forces. Okay, so like dissolves like. So water is able to dissolve many salts, so many ionic compounds, because the stronger ion, dipole attractions, that water forms with the ions of the salt are very similar to the strong attractions the ions themselves have. So the attractions between the ions is going to be very similar to the attraction between the ion and the pole on the water. But something like hexane is not going to dissolve into water because the water is going to be more attracted to itself than to that hexane. So the water will pull to itself. So oil does not dissolve in water. Oil is immiscible in water because those dipole-induced dipole attractions in the oil, they're not stronger than the dipole-dipole or the hydrogen bonding occurring in the water. So the water is more attracted to itself. Now, if we think about something that's a hydrocarbon with a polar end, so all of our alcohols, ethanol, anything that ends in -ol, those are all of my alcohols. So they're a hydrocarbon that has a polar end. These hydrocarbons, it depends on how big it is for which it's going to be more or less soluble with. Because when we're talking about something that's quite large of hydrocarbons, lots of C's and lots of H's, then it has a large area where it's actually nonpolar, and a very tiny area where you would call it polar. So as the hydrocarbon portion of the alcohol increases in length, okay, so as this nonpolar area increases, it becomes less soluble in water. Only the one tiny end is attracted to the water, or is the water attracted to it. The rest of it, the water has zero interest in. Oppositely, if I talk about an alcohol in a nonpolar solvent, so such as oil, if I put this in there and the larger the hydrocarbon region, the more soluble it becomes because more of it is nonpolar. So enthalpy of solution, delta H of solution. The enthalpy change is associated with the formation of a solution. The first thing I want to do is look at this picture. Okay. So the way we make a solution is we have a solute, we have a solvent. They already have their own attractions to themselves. That's what's holding them together. If I want to mix these together, I have to first break their own attractions to themselves. Remember the whole more attracted to themselves than to each other. So a great way to think about these is think about little magnetic balls that little kids play with, and you get to make different designs out of. If I want to mix the blue ones with the red ones, I have to first break them apart. So you add energy to separate your solute, separate your solvent, then the energy that's released whenever they all combine together in my new mixture. So to calculate this, it's in 3 steps. First, you have your delta H of your solute, which is going to be based off of its lattice energy if it's ionic, right? The energy required to separate the ions. Then you have your delta H for your solution. Both of these are endothermic. Energy must go into them to separate them. And then step 3, how much energy is released when they do combine? They go to a more stable state, so they're releasing energy. Whether or not overall it's endothermic or exothermic has to do with how much energy is being released versus how much energy do you have to add to actually make them mix together. So the last thing is just a hot and cold pack, and your OWL really covers this quite well. But you're going to use the same concepts of miscible and immiscible and the amount of energy released, all when you consider your hot packs. Okay? And you should be able to complete exercise 1 and exercise 2 now.